Hello, and thank you for viewing my presentation at the Rochester Institute of Technology's Undergraduate Research Symposium. I'm Lindsay Fiorelli, a third-year physics student, and today I will be presenting my research performed under the direction of Dr. Grover Schwartzlander about acoustic levitation. Acoustic levitation occurs when a sound wave exerts a force on an object, suspending it against gravity. These acoustic forces are normally weak in our everyday lives, but they can become quite strong when using high-intensity sound. Levitation can be accomplished with several different techniques, each having its individual advantages and disadvantages. Unlike other forms of levitation, like electric or magnetic, acoustic levitation has no limitation in terms of the properties of the materials it can levitate. It is optimal for small and lightweight objects. This technology is being applied to many different fields and is currently being used to study chemical reactions, X-ray protein structures, and to move delicate objects in robotics. In my research with Dr. Schwartzlander, we are using computer modeling and high-speed imaging to study the forces acting on levitated water droplets. Our objective is to use acoustic levitation as a platform to study droplet interactions with lasers. In our work, we are using standing wave levitation, in which particles are trapped at the nodes of an acoustic standing wave. Our single-axis acoustic levitator consists of two main circular parts, vibrating transducer and the reflector, both arranged with their coaxis in the gravitational direction. The transducer vibrates, creating a 20 kHz planar pressure wave. This frequency sits right at the edge of the human hearing range, so while the intensity is close to that of a rock concert, only a mildly annoying high-pitched whine is audible. Still, we layer up the ear protection just to be on the safe side. The acoustic wave travels through the observable plane to the reflecting plate. The wave is reflected off the plate and causes interference. By setting the plate a multiple of 1/4 the sound's wavelength from the transducer, this interference emerges as a standing wave with nodes and antinodes. Levitated particles will avoid the antinodes in favor of the stable, low-pressure nodes.
I introduce the water droplets to the system by deploying a fine mist of what we call microdroplets across the observable plane. As you can see, the droplets avoid the antinodes entirely, settling vertically at the nodes. Slowly, the droplets accumulate in the horizontal direction as well, becoming one large central droplet at each node in the plane. The acoustic trap is clearly much stiffer in the vertical direction than the horizontal direction. Our goal is to soften the trapping in the horizontal direction even further while maintaining the strong vertical trap so that external forces could potentially interact with the central droplet, allowing for free movement side to side.
In order to better observe droplet behavior in the trapping zones, we use an edgertronic high-speed camera. The high-speed camera sits horizontal from the node of interest, where it can capture all the droplet activity at that node.
The fast camera shows how the dominant droplet continues to grow in size when supplied with a stream of microdroplets. As seen in other research, the droplet becomes elongated as it grows owing to strong vertical forces and weak horizontal forces. When the acoustic forces exceed the surface tension, the droplet bursts. In order to avoid having to factor in the so-called Bernoulli pressure produced when the particle elongates, we use particles with less density that will maintain its spherical shape. The droplets exhibit a variety of interesting and unexpected behaviors that I hope we will be able to explore as we continue our research.
Returning to our main objective, the effective trap stiffness for both the horizontal and vertical directions can be characterized by finding the restoring force of the trap. This is easy enough to see in the X and Z directions, but tracking the particle's displacement in and out of the Y direction became a challenge. Rather than using a multi-view synchronized camera system to track the droplet's displacement, we prefer to retrieve displacement data from a single camera by means of a trained artificial intelligence system. For this reason, we began working with Dr. Giovanni Volpe and his graduate student Benjamin Midvet at Chambers University of Technology located in Gothenburg, Sweden. Dr. Volpe has been developing artificial intelligence methods for tracking particles in similar systems. Though the collaboration was put on hold due to the COVID-19 pandemic, we were able to receive some preliminary results.
The video tracks a 1 millimeter diameter droplet as it travels in and out of focus in the field of a dilated laser beam. The trained network analyzed the focus as well as the laser's refraction to graph the displacement of the droplet in the y direction. In the graph, the full line is the predicted y position of the droplet, and the dashed line represents the closest sine wave.
Altogether, the analysis was successful in proving that our collaborators' tracking system is compatible with our experimental setup, and the challenges that arose can easily be solved. In the future, we'd like to explore tracking a droplet entirely out of focus, as well as tracking a droplet that's been mixed with fluorescent dye.
Our simulation models the acoustic standing wave produced by the transducer located at 2.5 wavelengths from the reflecting plate. We use two pressure wave sources, one source being at the horn of the transducer and the second at twice the separation distance to simulate the mirroring effect by the reflecting plate. The graphs only depict the activity in the observable plane between the transducer and the reflecting plate, as seen here. The graphs of the acoustic pressure and the acoustic pressure gradient at various points along the observable plane come out as expected at this separation distance. However, we run into a problem at other separation distances. We expect the interference not to create a standing wave when the separation distance isn't a multiple of 1/4 of the wavelength. However, in this video that represents the pressure field at different separation distances, it is clear there are nodes and antinodes in each. To solve this, we will be adding more pairs of sources to the system, creating a more real-life setup.
Since the droplet acts as a harmonic oscillator, we can estimate an effective trap stiffness based on the measured period of oscillation in the approximate mass of the droplet. An effective value is used because the droplet is driven by the acoustic field in a sustained oscillation and is not freely oscillating. By extracting the period of oscillations in the x and z directions, we find an x direction period of 0.3 seconds and a z direction period of 0.05 seconds for a droplet of about 0.5 milligram. The effective trapping stiffness K is determined by this expression, from which we determine the x and z stiffness. As expected, the acoustic trap is much stiffer in the vertical direction than the horizontal direction, 40 times stiffer in this case. Here we note that an equivalent radiation pressure force from a laser focused on the droplet would require a laser power on the order of 100 watts. A more modest power of 10 watts would produce a measurable result, affecting the oscillation amplitude and the period. Therefore, we conclude that an acoustic trap may provide a means of studying laser-driven optomechanical droplet dynamics. Our challenges moving forward are to understand more about the acoustically driven oscillation, determine if the motion is regular or chaotic, and explore means to reduce the values of horizontal stiffness.
Special thanks to my research advisor, Dr. Schwartzlander, and collaborator, Lucy Chu, as well as the Rochester Institute of Technology for the opportunity to present my work. And thank you for taking the time to see my presentation.